let me talk about arguably one of the most popular quantitative interests for interpreting results from multinomial logic models, as well as, if you recall, binary logic models and proportional odds order regression models. Okay? The motivation is as follows. The discrete change is useful, but is limited. Same case for partial change. At different levels of the variables, the discrete change or discrete rates of change will be different. Same thing for partial change. If we change the values of variable of our interest, in this case, generic variable, right, xk. Let's say we want to study the partial change, right, of xk. If we change the values of xk, or if we change the values of other covariates, then the results, that is discrete change, partial change, marginal effect, going to be different. So they are location what? Dependent, okay? How about a quantity that is location free? We don't have to worry about where the values of our covariates are held, and we can study the effects of these covariates. Well, discrete change or discrete rates of change does not indicate the dynamics among the dependent variables. For example, a decrease in education increases the probability of both poor and fair health. But how does it affect the odds of a person having poor relative to fair health? To answer these questions, consider the multinomial logic model as an odds model. So if you recall, when we derive the multinomial logic models, it can be expressed as a series of binary logics or odds model, right? So in this case, let's focus on this odds comparison. That is lowercase m, a generic response category of y versus the reference category, capital letter M. And if we want to figure out the effect of x2 on odds comparison, well, the equation can be expressed as the multiplication or the product on the right to the equality sign. So this is very generic. This is a very generic equation, right? Expression. So on the right is basically exponential of x beta, right? From intercept to beta 0 to beta 1, x1, beta 2, x2, beta 3, x3, and we can go on, right? Depending upon how many covariates we have. And in this case, odds comparisons are what? This generic category, lowercase m versus the capital letter M. If x is changed by 1 unit, okay, so we add 1 unit to x2, what's going to happen? Well, we just expand these terms, right? For x2 in this term, we have 2 terms, 2 product terms, right? Because once we add 1 unit to x2, we get additional term for beta 2, lowercase m over capital letter M. Okay, so that is outcome, okay, the result we will get by increasing x2, a generic variable. It does not have to be x2 by 1 unit. Then effect of x2 can be measured by the ratio of odds, accordingly odds ratio, right? So if we take a ratio of these 2 odds, you know, in the numerator is the odds after we increase x2 by 1 unit. In the denominator is this original odds. After we take a ratio of these 2, then we get this single term, right? That is natural exponential of beta 2, right? that is slope coefficient for x2. Okay, for the odds comparison of lowercase m versus uppercase m. Okay, well, this gives us a very, very handy and powerful interpretation of the effects of a generic variable xk. In this case, is x2, right? In this case, we're going to say, well, for each unit increasing x2, depending on the substantive unit of x2, we would expect odds of what a generic category lowercase m over the reference category uppercase m is going to change by a factor of e raised to the power of beta 2. Well, what is beta 2? Well, that beta 2 is regression slope coefficient for x2. What is x2? x2 is the variable of our interest for the odds comparison of lowercase m versus capital uppercase m, right? So if we replace x2 by a generic variable xk, what we're going to say, well, in this case, we're going to say, well, holding all other variables constant. In this case, we kind of, cancel out the effects or the interference of all other covariates, right? So we're going to say, well, holding all other variables constant for each unit increasing xk, we would expect odds of, well, we have to be very clear about odds. Odds is lowercase m versus uppercase m. Again, that depends on the kind of substantive odds comparisons users have for their substantive question, right? So the odds of lowercase m versus uppercase m is going to change by a factor of e raised to the power of beta k. So here beta k is the slope coefficient for xk variable. In this case, for the odds comparison of our interest, that is lowercase m versus uppercase m. Okay, let's continue. So the odds ratio can be interpreted as for a unit change in xk, odds are expected to change by a factor of e raised to the power of beta k for the odds comparison of lowercase m versus uppercase m, holding all other variables constant. Okay, remember the factor change in the odds does not depend on the level of sk or on the other level of any other variables. That's the reason why we can say, well, holding all other variables constant. It doesn't matter where we hold these covariates to. Okay, so that is the beauty of odds ratio interpretation. Okay, the same holds for an odds ratio interpretation in proportional odds model as well as binary logit model.